Hello and namaste everyone. Welcome to this last week of this NPTEL course on stochastic approximation. In this week we will do a recap of some of the important concepts that we have covered throughout this course and that will help summarize what all different things we have done, and also help you prepare for the exam if you are planning to register for this course and give an exam. Okay, so let us begin today's discussion. Okay, so if you remember, in this course we started out by going over some background material such as probability, ordinary differential equations, a bunch of concepts from real analysis, and then we moved on to stochastic approximation. So in this lecture and the next we will be covering some of these basic stuffs. So in today's class we will be focusing on probability theory, and let's begin that discussion. So one of the important concepts within probability that we encountered was that of a sigma field. So let me recall for you what a sigma field is, right? So if S is a set, then a sigma field on this set S is a collection F of subsets of S, right? So if S is a set, then a sigma field is a collection of subsets of S, and this collection of subsets needs to satisfy certain properties, right? In particular, it needs to satisfy the property that the whole set S belongs to this collection. Furthermore, we require that this collection be closed under the complement operation. By that I mean, if this collection has a set A, then we necessarily require that set A complement also be in F. Furthermore, we require that this collection be closed under the union operation, countable union operation. So by that what we mean is, suppose you have an belongs to F for all n in the set of natural numbers. So if you have a collection of A sets, subsets of S such as A1, A2, A3, and if all of them belong to our collection F, then we require that the countable union of these sets also belongs to F. So in this sense we require that your F be closed under the countable union operation, right? So here is a simple question that one may ask in the context of sigma fields. So let's say S is the following set. So it consists of three elements A, B and C, and let us say we have been given a collection of subsets of S. Now for any set S, your empty set is a trivial subset, and then we have three singleton sets, that is the set containing A, the set containing B and the set containing C, right? And the question asks us to check whether this collection is a sigma field or not, right? So in order to check this, we have to see if all these three properties indeed hold true or not. So if you go through the list, one can immediately see that your S, which is ABC, is not present in this collection. Okay, so that is one reason because of which one can easily conclude that this collection is not a sigma field. However, there are several other reasons because of which F is not a sigma field. For example, we also require that your set F be closed under complements, but one can see that although the set containing A belongs to F, its complement, which basically includes the elements B and C, okay, that set, okay, does not belong to F. So I should perhaps emphasize here that this does not belong to F. Similarly, while the singleton set containing B belongs to F, its complement, which includes A and C, that does not belong to F, and so on and so forth. Okay, so you can see that there are multiple reasons because of which this collection F is not a sigma field, and I have highlighted here two reasons, right? And one can see that the answer to the previous question is that the collection F is not a sigma field, right? So the other important concept that we have covered during this course is that of a random variable, right? And towards that we introduced some notion called as a measurable space, right? So what is a measurable space? Well, it's a set S along with a sigma algebra or a sigma field of subsets of S, right? So when you have this pair, that is the set S and a collection of subsets of S, we will say this pair forms a measurable space, right. So given a measurable space, a random variable associated with this measurable space is a map, right, is a map or a function such that the domain of this function is S, which is the same set over here, and the codomain or the range of this function is R, right. So not any function is a random variable. For a function to be a random variable, it needs to be measurable. By that, what do I mean is that this condition needs to be satisfied. So what does this condition say? It says that the inverse image of A should belong to F for every A in the Borel sigma algebra, right. So Borel sigma algebra is a collection of subsets of the real line which together form a sigma field, right. And the nice thing about this sigma field is that it includes sets of interest. For example, your intervals of different kinds, that is your intervals which are open at both ends, for example something like this, right, or intervals which are closed at one end, right, or closed at both ends, and so on and so forth. So all such kind of intervals, okay, they belong to this Borel sigma algebra, right. So this is why it is special. So Borel sigma algebra in some sense is the smallest sigma algebra that contains sets of this form, right. And for x to be a random variable, we require that x inverse of A belong to F for every A in B of R. And I would like to highlight here that typically when we talk of inverse functions and so on, we require that the original function be bijective, that is it should be 1 to 1 and onto, and only then we talk about the inverse of a function's existence, right. However, here when we are saying inverse, we actually don't mean the inverse of the function, but rather what do we mean here is that it is the pre-image, right. So let me write it over here. This is the pre-image. So what do I mean by pre-image? For any subset A of R, x inverse A is the collection of all omega in S such that x of omega belongs to A, right. So for example, if your, let's say your original set is 1, 2 and 3, and let's say this is S and this is R, and let's say, or let me instead of labeling it as 1, 2, 3, let me label it as A, B, C, and let's say A and B map to 1 and C let's say maps to 2. So in this case, x inverse of let's say the interval 0, 1. So I hope you agree that the interval 0, 1 is a subset of R, and I am asking if this is your map X, what is x inverse of 0, 1. So we have to go to S and identify all those points which map to 0, 1. So one can see that in this case both A and B map to 1, hence x inverse of this closed interval 0, 1 will be A and B, right. So in this way one can see or one can define this pre-image. So let me quickly summarize. Let S comma F be a measurable space, then a random variable is a function x that goes from S to R with the property that x inverse A must belong to F for all A in B of R, where x inverse of A is defined in the following sense, right. So here is a question associated with random variables, right. So the question says let x be a constant real valued function on some sample space S, right, and it asks is this x always a random variable or not, right. So first let's understand the question and let's see what is the challenge, right. So what it says is that x is a constant real valued function. So what it means is that x is a function from S to R, so that S is a sample space, so x is a function from S to R, and for every omega in S, x of omega takes the same value, and let's denote that same value by C. So C is some real number, and for every omega in S, x of omega is C, and hence we will say that x is a constant real valued function, right. And the question asks us whether such a function x, is it a random variable or not. So the missing part or the the puzzling part of this question is that we have not been given any sigma field, right. So that is the puzzling part. So the question is, without being given the sigma field, how do we decide whether this function x is it random variable or not, right. So the first thing to keep in mind is that every sigma field, whatever be the sigma field, s will always be in f, right. So because that is the key property of your sigma field, that whatever be the sigma field under consideration, s will always belong to f. Furthermore, it needs to be closed under complement operation. So which implies that whatever be the underlying sigma field, the empty set and the whole space, which in this case is denoted by s, will always belong to f, right. So whatever be f, the empty set and s will indeed belong to f. Now let us consider any a in B of R, right. So if I look at the pre-image of this set capital A, I hope you agree that if this little c, whatever is this little c, is not part of A, then x inverse of A will be empty, because there is no element in S which under x, the function x is mapped to A, and hence x inverse A will be the empty set. On the other hand, if this element C belongs to A, then x inverse A will be the whole space, because every element in S is mapped to C, and C is an element of A, which implies that x inverse A will indeed be S. So from this what we can conclude is that whatever be the sigma field, if you have a constant real valued function, then for any A in the Borel sigma algebra on R, x inverse of A will either be the empty set or it will be the whole sample space, right. And these two elements will always belong to F, and hence one can conclude that even though we have not been given the sigma field, whatever be the sigma field, your x inverse of A will be part of that sigma field, and hence one can conclude that x will always be a random variable. Okay. Now let us move on to one more interesting concept that you should know as part of probability, and this is some inequality which is referred to as the Markov inequality. So I will prove this inequality and try to give some application of this inequality, right. So what does this inequality say? It says that suppose x be a non-negative random variable such that its expected value of absolute value of x is less than infinity, which means that this random variable x is integrable, okay, and since it is non-negative, absolute value of x will basically be expected value of x itself, okay. So let x be a non-negative random variable, and let us say its expectation is finite, right. Then what Markov inequality says is that for any a greater than 0, the probability that x takes a value above A is upper bounded by expected value of x divided by A. Is this okay? So this is what Markov's inequality tells us. So sometimes this ratio will be bigger than 1, in which case this bound is vacuous, because we know that for any event the probability is less than 1. However, there will be certain circumstances where this bound could be less than 1, in which case this provides some insight on what could be the value of probability x bigger than equal to A. So what I am going to do now is to first prove this inequality, right, and then discuss some application of this inequality, right. So how do we go about proving this inequality? Observe that any random variable x can be written in the following way, right. So when I write something like this, recall that x is a function. So what do I mean is that whatever be the input, the output of x will either be described by this part or by this part. So let me elaborate, okay. So when I give omega as input, okay, for this omega, either x of omega will be less than A, or x of omega will be whatever be omega, x of omega will either be greater than A or it will be less than A, right. So if it is greater than A, then this indicator will be 1, and this indicator will be 0, hence x of omega will be x of omega times this indicator, which is 1, and consequently this equality will hold. On the other hand, when x of omega is less than a, strictly less than a, then this indicator will be 0, whereas this indicator will be 1, and hence x of omega will equal x of omega times 1, and hence this equality will hold in this case. Now for any omega, x of omega can either be bigger than a or less than a, and hence one can conclude that this equality holds, right. Now from the linearity of expectation, right, and since all these are non-negative random variables, and linearity of expectation holds true for non-negative random variables, one can show that the expected value of x equals the expected value of this plus the expected value of this, right. Now since x is a non-negative random variable, one can conclude that x is greater than or equal to 0. By that I mean that x of omega is greater than 0 for all omega, right, and hence this inequality over here holds, right. So x times indicator this basically means for any omega, this is x of omega, indicator x of omega strictly less than a, right. So this product actually holds, right, and hence what I wanted to say was, since x of omega is greater than or equal to 0, this product is greater than or equal to 0. In other words, this function is non-negative, and since this function is non-negative, one can conclude that its expectation will also be non-negative, right. And we have shown here that the expected value of x is the expected value of this quantity plus this quantity, and we have just now showed that the expectation of this quantity is greater than or equal to 0, from which we can therefore conclude that the expected value of x must be bigger than the expected value of x times indicator x greater than or equal to 0. Now what I am going to show is that the x times the indicator x greater than or equal to 0 is bigger than this quantity. So let us see why this is the case. Again the idea is to break, like this is a function on the left hand side, okay, so this is times this indicator, and similarly this is a times this indicator. So you have some function on the left hand side and some function on the right hand side, and what we are claiming is that for every input omega, the left hand side is bigger than the right hand side. So let us see why that is the case. So for any omega, either your x of omega is bigger than a or x of omega is less than a. First let us consider the easy case, that is x of omega is less than a. Now if x of omega is less than a, then this indicator is 0 and this indicator is 0, which implies that both the right hand side and the left hand side are 0, and hence 0 is bigger than or equal to 0 is what equation 1 is telling us, which implies this equation 1 indeed holds, right. On the other hand, suppose x of omega is bigger than a, then the left hand side is x of omega times this indicator, and this indicator is 1 because x of omega is bigger than or equal to a, which implies that x of omega is the left hand side. On the other hand, the right hand side is simply a, right, it is simply a because this indicator is 1. Now we know that for this omega, x of omega is bigger than or equal to a, and hence the left hand side is indeed bigger than the right hand side, which implies this inequality again holds true. So we have seen that for whatever omega, either this is true or this is true, and in either of these cases this inequality holds, from which we can conclude that this inequality holds for every omega, right. So this inequality, since it holds and since your expectation is monotone, one can conclude that the expectation of this quantity is bigger than the expectation of the quantity on the right, which is exactly what I have written over here. And since this expectation is bigger than this expectation, and since this expectation is from the linearity property, you can pull out the a outside, and the expectation of an indicator is probability of x bigger than or equal to a, we can conclude finally that expected value of x is bigger than a times probability x bigger than or equal to a, right. And since a is strictly bigger than 0 as per the conditions given in the theorem, one can conclude that probability x greater than or equal to a is less than expected value of x by a, right, which is the quantity or which is the relation that we wanted to show, right. Now let us see a question based on Markov inequality. Suppose x is an arbitrary random variable, then the claim is that for any epsilon greater than 0 is probability x bigger than mu plus epsilon less than equal to variance of x by epsilon square, where I should perhaps add where your mu is expected value of x. Okay, and we will presume that these expectations and variances are finite for this inequality to make sense. Okay, so first let's see if we can directly apply Markov inequality to the left hand side, and whether can we conclude that probability x bigger than mu plus epsilon. So perhaps we can think of this as A and maybe use Markov inequality to conclude that probability x bigger than mu plus epsilon is less than equal to expected value of x by mu plus epsilon, right. So if you try to think of such approaches, you would be wrong. The reason being, recall that the Markov inequality applies only if this given random variable x is non-negative, right. Now here x is some arbitrary random variable, so we don't know whether x is a non-negative random variable or not. Hence we cannot make use of an inequality of the following kind, right. So that is the first observation, that look, you cannot blindly apply Markov inequality because your Markov inequality only applies to non-negative random variables. Okay, so the question is, okay, how can we then apply Markov inequality to get some inequality like this? So towards that, what we do is, the first observation we make is this event, that is the collection of all omegas where x of omega minus mu, the absolute value of that is greater than epsilon, can be written as the union of this pairwise disjoint events, which is that x minus mu is greater than epsilon and x minus mu is less than epsilon. So if your omega is such that this is bigger than epsilon or this is less than minus epsilon, then one can conclude that for that omega, the absolute value of x minus y is greater than equal to epsilon, and vice versa. That is, if this is greater than epsilon, either this holds or this holds. So from that part one can see that this equality indeed holds, and importantly these are pairwise disjoint events, right. Okay, so one can then see that, so I have made a typo here, this should be union. So one can then see that this event can be written as x greater than mu plus epsilon. Similarly this event can be written as x less than equal to mu minus epsilon, right. So since these are pairwise disjoint or mutually exclusive events, one can conclude that the probability of the event on the left hand side must be the sum of probabilities on the right hand side, which is that probability of absolute value of x minus mu greater than equal to epsilon is equal to probability x greater than mu plus epsilon or probability x less than mu minus epsilon, right. And consequently one can conclude that because this event has non-zero probability, I mean any event has non-zero probability, hence one can conclude that the probability of this event, which is what we have over here, is less than equal to the probability of this event. In other words, this probability must be greater than this probability, and this is exactly what we have written over here. Now the nice thing about this probability of this event is that this quantity over here, okay, or the random variable that is over here, because of the presence of your absolute sign, right, becomes a non-negative random variable, right. So indeed we can apply the Markov inequality over here. However, we can, if we directly try to apply the Markov inequality over here, what we would end up showing is that this quantity is less than equal to absolute value of expected value of x minus mu by epsilon. This is what we would manage to show. However, if you go back to the previous question, what we have been asked is to show that this probability is less than variance of x by epsilon square, right. So even though we can apply Markov inequality here, we see that we don't get necessarily the same kind of bound that is expected as part of the question. So then what we observe is that this event is basically equal to this event, right. So whenever a non-negative term, which is non-negative because of the presence of the absolute value, so if this non-negative term is bigger than epsilon, right, then for any such omega the square must also be bigger than epsilon square, and this statement goes in this direction as well, which is that if this thing holds true then this must hold true, from which we can conclude that this event and this event are one and the same, which means the probability of this event and probability of this event are one and the same. And the nice thing about this event's probability is that again this random variable over here is non-negative, and we can apply Markov's inequality here to conclude that the probability of x minus mu square greater than epsilon square is upper bounded by the expected value of x minus mu the whole square by epsilon square. So if you think of this as the random variable and this random variable is non-negative, you have to take the expectation of this random variable and divide it by whatever quantity you have over here to get this quantity. However, the expected value of x minus mu square is indeed variance of x, which gives us the desired expression. So in conclusion, what we managed to do was we showed that probability of x bigger than mu plus epsilon is upper bounded by probability that the absolute difference between x minus mu is greater than epsilon, and this quantity we said is equal to the probability of this event, and by using Markov's inequality we managed to show that this is upper bounded by variance of x by epsilon square, right. So one can see that by doing a series of manipulations and taking the Markov inequality at an appropriate place, we indeed get the desired bound. Okay, so this brings us to the end of this class. So let me summarize what we have done. We went over some basic concepts of probability. In particular, we went over this concept of sigma field, then we went over this idea of random variable, and then we went over this idea of Markov inequality. We proved this Markov inequality and also looked at some extension of this Markov inequality, and in particular we derived this inequality which said that probability x bigger than mu plus epsilon is upper bounded by the variance of this random variable by epsilon square, right. If some of you have seen this inequality, you will immediately see that this is some form of what is popularly known as the Chebyshev inequality, right. So one can see that some of these popular inequalities have been derived by can be derived by making use of this very powerful Markov inequality. So in the next class we will look at few more concepts, review few more concepts that we have discussed during this course. Until then, goodbye, namaste, and hope to see you soon. Thank you.